All right, inductive definitions. So, by the way, do you remember mathematical induction? Is everybody familiar with that concept? It was, you know, I'm not sure to how advanced you would be in high school, right, in terms of mathematics. What did you learn about mathematical induction? In high school, in the first years of college?
Okay, so I think we've all taken a prerequisite course, it's called proof. So basic induction was covered.
I see, all right, okay. So let's remember that very quickly. How does it work?
You can start with a base case.
So we start with a base case, right? The most basic of base cases would be the one for the number 0, right? It generally applies to the set of natural numbers, right? And what we want to do is expand inductive reasoning. So we're going to see shortly how, but let's just remember. So we want to prove a property. That's our goal, right? For all n, we want to prove P of n. We want to prove that this is true, right? And the way we do this is we first start by proving P, let's say, of 0. We can pick another number. But this n, if we pick all n here, we should start with P0, right? And then we also prove that for all n, Pn implies Pn plus 1, right? And this seems sort of like magic, because if we manage to prove these two clauses, which are typically very simple to prove in most situations, we have proved this, right? That something holds for all n. And why does this work, right? There's a very simple intuition. We have just proven that P0 works, right? And then if I plug P0 here, I'm going to get that P1 works. P1 is true, right? And then now that I know that P1 is true, I'm going to plug P1 in here, and I'm going to find out that P2 is true, right? And I can go like this ad infinitum. I can go it like this forever, right? But any number, whatever number, bounded finite number I pick, I will find a chain of reasoning starting from 0, showing me that if P0 holds, then P1, then P2, and let's say my number is 1,000,001, so I'm going to find out that P of 1,000,001 holds, right? Because in practice, we're never interested for all n, right? We're interested in having the comfort of picking any finite n and having something hold for that number. Right, so infinity is just a cover for an unknown finite number. Okay, so once we've done that, and let's do a little side here. Have you studied philosophy? In some places it is required as a first year course, right? When I was a freshman, it was, right? And you might remember there are two ways of uncovering new knowledge: induction and deduction, right? So mathematical induction, where does it fit? Is it a form of induction or a form of deduction?
It's a form of deduction.
It's a form of deduction, right? Very good. So mathematics doesn't do induction. Induction is the kind of reasoning where I see there's this famous phrase, right? All men are mortal. Socrates is a man. Therefore, Socrates is mortal, right? This is an example of modus ponens, and it's a form of deduction, right? So let's do the reverse. Socrates is mortal, and Socrates is a man. Is it the case that all men are mortal? Obviously not, but we can conjecture that. We can wonder, well, might it be the case that all men are mortal, right? So this is a form of induction. We are creating a conjecture, not an established truth, but then we can go and verify that truth, right? And in this way, we gain new knowledge. So this is what really in philosophy induction is. Why the creators of mathematical induction did they call it induction? Because it looks like magic, right? Because it looks like uncovering new truth from something that is not obviously indicating that truth. So they thought that induction is appropriate. Nevertheless, remember, it's a form of deduction, and mathematics only does deduction. Now, this establishes a very interesting form of reasoning, because we have a structure to this reasoning. And we're going to see shortly that data structures have very much in common with natural numbers, and then we have a form of inductive reasoning for data structures. And this is what really is of interest for us. Okay. So, how do we define infinite sets? Because if you think of all the data structures, it's not that they're infinite, right? They're not really infinite. It's useful to think of them as if they were infinite. Infinity is a convenience. Remember, it's not a complication. Infinity simplifies things in mathematics. It doesn't complicate, right? And often, by thinking in terms of infinity, you take a detour from reality, and you get types of reasoning that do not really apply in real life, but it may help with getting to the truth a bit faster, or getting to an approximation of the truth a bit faster, right? So we tend to think of data structures as an infinite set, right? If we think of all the lists, of course, each and every list inside there is finite, but the set of all of them is infinite, right? Why do we think of them as infinite? Because we're not going to know upfront the limits of memory in our system, right? So I don't want to add the burden of putting such a limitation to my reasoning. I'm going to say, oh, since I don't know how much memory I have, I might as well think that I don't have a limit in memory. Then any size of a data structure is possible. And therefore, let me think of the entire set of data structures which turn out to be infinite. And then we want to define them, and we want to reason about them, right? How do we define an infinite set? And the answer is, so we saw previously that we reason about infinity. The set of natural numbers is infinite, and we reason about it with induction. So we're going to use inductive reasoning to create infinite sets and reason about them. The simplest inductive definition is that of natural numbers. And it comes from a person named Peano. Have you heard of that? You took logic, right, and proof. Italian mathematician, beginning of 20th century. So at that point, there were quite a few people trying to formalize arithmetic, right, and natural numbers. They seemed to be the simplest form of numbers, and they wanted a formulas. And this is the guy who won the contest, who got it right. So he created a formalization for natural numbers, and he defined basic operations like addition and so on. And he did it in the following way. He said, well, there's this element 0 that I pull out of thin air, my universe of infinite objects. There's one that I distinguish and call 0. And then, if n is a numeral, so is the successor. I have this function called successor that gives me the successor of a natural number, of a numeral. All right? So then, based on these rules, I can very easily decide that 0 is a natural number. Then successor of 0 must be a natural number as well by the second rule. And since successor of 0 is a natural number, successor of 0 must be a natural number. And then successor of 0 must be a natural number, right? And these are my natural numbers. You're going to say, what's the big deal? First of all, where are the 0, 1, and 2 that we know from elementary school? Well, those are just notations for something that we are constructing. Those are just names. Those are just symbols that make our life easier. But what natural numbers are, says Peano, and we might find it useful to believe him every once in a while, whenever it's convenient. There are other theories of natural numbers as well, but whenever it's convenient, we're going to put ourselves in Peano's shoes, and we're going to say, yes, the set of natural number is this very odd-looking set, right? So if I would look at it as a set, it's Z for 0, successor of Z, successor of Z, and I can go on forever, right? This is my infinite set of natural numbers, and the digital representation of those numbers is just a convenience, it's just a notation, those are just names. Right? In reality, I will have to structurally decompose numbers to look at their value. What about this successor function? Okay, this is what we call a constructor. It is something that doesn't provide any computation. You see, the number 1 in this theory, I cannot write anything but successor of 0. I cannot say, oh, successor is this function that does a computation and returns me a result. The expression is the result. Successor of 0 is the result. So this kind of function we call a constructor in general, right? It doesn't provide computation, it just provides syntactic structure. And if you remember you're a camel, you have seen this before, right? We're gonna look at definitions shortly. So I'm gonna try to go through this in a camel at the end of the class and clarify a few things so that you're prepared mentally for what's coming. So we have defined an infinite set, right? Every element in there is finite. Nevertheless, the set is infinite. Whatever subset you take, you can take the maximum, you put another successor, and you create yet another element that is not yet in the set, right? So you can continuously add elements to that set. Therefore, it is infinite. How about other inductive definitions? Is there anything else that shares this kind of structure? And by the way, I'm going back to arithmetic and natural numbers just because it's a very convenient example, and our coding will never use that kind of encoding for natural numbers. We already have a very efficient hardware encoding, which most programming languages would provide access to, and we were going to use that one. This is just for illustrating a principle. So as much as we won't be using natural numbers in Peano's representation, many other data structures share the same kind of structural definition, and there's nothing else we can do to it, so we have to use it. For instance, trees. How would we define the set of binary trees? Think of it again, it's infinite. Every tree is finite, but if I get 2 trees, I can make one the left I can create a completely new node, make one of the given trees the left child, the other one as the right child, and I have a new tree which is deeper, larger, right? So at least in height, trees will be infinite, and therefore the set of all trees has to be infinite. How do we define such a set of infinite trees? Well, very easily, following the previous example. There is this object that I pull out of thin air, I call the empty tree. Okay? And then I have this function called node, which is a constructor, and given 2 trees, L and R, we create a new tree, which is node of L and R. Okay? And then this is a weird kind of tree, if you want. There are many types of trees. And again, this is illustrated this is just for purposes of illustration. This is a tree that doesn't have anything at the inner nodes, right? So it's empty inside, but at the leaves, it will have, not even the leaves have anything, right? So this is a tree that only has structure. It doesn't have information inside, right? But it nevertheless looks like a tree, not necessarily a useful one, and it is an infinite set, and it can be defined like this, okay? And it will have this very weird looking expression, and we cannot replace it by anything, right? Because the node doesn't, as a function, doesn't return a value. So something like node empty empty, this sub-expression here, is its own value. Cool. Now, we tend to be a little bit more concise in our presentations. We want a bit of syntax added into the mix so we can make our rules a bit more concise. We're going to work with rules that look in, I have this format. We draw a bar. Above the bar, we write a premise, something that is assumed to be true. And under the bar, we write the conclusion, something that is a consequent of the premise. Is necessarily true only if the premise is true. And the best example is this one is the more complicated one, because here you recognize the rule whereby if n is a numeral, then the successor of n is a numeral. So only if n is a numeral, then the successor of n is a numeral. However, we also have rules that have no premise. So they are axioms. They are true unconditionally, right? And this rule over here is an example. There's nothing above the bar, and therefore 0 is a numeral no matter what. So the two sets of rules that we have seen, one for numerals and one for binary trees, we both show them here. We've seen the one for the numerals. Let's look at the one for the binary trees. Here we're going to say that empty is a tree unconditionally. And then if TL is a tree and TR is also a tree, then node TL, TR is a tree. Right? So instead of writing everything in English as in the previous two slides, we can just put our rules in this form, and it's shorter and clearer. Are there any questions so far? No? Simple stuff, right? So we can actually have an even more concise form, because previously we were saying that, oh, there's this set of numerals, but in this shorter format we're saying that, oh, 0 is a correct syntactic construct, and then if n is a correct syntactic construct, then suc n is a correct syntactic construct, and that's it. We don't need to mention the set. The same for trees. If empty is a syntactic construct, correct syntactic construct, and then if TL and TR are correct syntactic constructs, then node of TL and TR is a correct syntactic construct. And we're going to use the shorter form quite frequently. Okay, so now there's the more complicated question. I'm going to go into something that's a little bit more hairy, just for the sake of an argument that I want to make at the end. So we are actually expressing, since you have studied proof, right, have studied a bit of logic, we are expressing a deductive rule here, right? And deductive rules, you can't really play with them, right? You can't really restrict them. They will give you whatever they will give you, right? So the question is, what is the set of all elements in the given universe that is closed with respect to those rules? So if I were to create a set of elements, subset of the given universe, right? And obviously, for that set to be num, let's go back here because we have the we have the num here, right? So if I were to have a more descriptive form of num, right? What would I put in here? Obviously, I have to put 0. Okay, I have to put successor of 0. Maybe I should just say z. How does it look on the screen? SZ, right? And ISSZ, and I can go on. And is that all I can put in? So I want you to imagine the following construction. S, apply to S, apply to S, apply to S, apply to, and you go on forever. Now you might want to say, well, does this term really exist? Well, we can't really refute its existence. We don't have an argument to say it doesn't. Now, if this term is a numeral, if I put this term, and I'm going to denote this by infinity because it kind of looks like infinity and it's a convenient form. So if I put infinity here, does this break the rules? Well,
is there
yes.
Is there a z inside that?
We don't know. We have no way of checking.
Can you do successor infinity?
If I put successor here, yes, what do I get?
You get successor infinity and you keep going on and on.
Is this true?
It breaks the rules, right?
Why?
Does it?
Well,
There's a number and its successor has to be
close.
distinct.
No, you just have to show that S infinity is also, so that S operation is closed under the set of elements.
Exactly. Yeah. So I'm going to have to verify these two rules with this set, but I want to put infinity here, right? Does that break the rules? In what way?
Because it doesn't build from n to the successor.
But I'm not saying that it has to build from n. I'm saying that if n is a numeral already, S successor of n should be a numeral, right?
But we are assuming that infinity
So
is
that's
a numeral.
the thing, right? If the successor, whatever that construction is, and you call that infinity, is a number, then there has to be an n, the successor of which will give you that number, infinity, right?
Yes.
If you cannot find such a number,
But I'm asking you, what is this?
that is infinity.
It's infinity, right?
Yeah,
So infinity is its own successor, right?
Yeah, but
right. But the rules don't refute that, right? The rules don't.
They
refute that.
exactly, right? So did I break the rules by putting infinity here?
No, you didn't.
So I didn't, right? That's an interesting thing, right? So I have a num infinity here, less denoted by num infinity, which is this set, and I have a simple num, which is the set without infinity. So it starts from 0, and it just goes on. There's no infinity in here, right? Are both of them solutions to my set of rules? Yes. Go ahead. Don't. Let me
Yeah, I
ask.
have a little bit of confusion.
Uh-huh.
I understand your reasoning there, right? But what I was trying to say was that if you consider that proof by contradiction, right? I mean, that entire thing is a numeral. Then there exists a smaller numeral, or there exists a subset of that, which is already a numeral. That's the only way that it becomes a numeral, right? There is some subset of those series of operations
Uh-huh.
that is already a numeral.
Right.
But if you go one level in, then you get infinity, and then you have that circular chain of reasoning, which
Right.
means that you cannot see a number n, a numeral n, for which the successor of n will give you infinity.
Yes, I
Therefore,
can.
it's a
Yes, I can. Infinity is.
But you haven't accepted infinity into the numerals.
But I'm
Why
not.
is reasoning?
It's not a rule of acceptance, right? I'm not. The rules are not saying that you have to be constructive. So you're trying to add, and that's actually a valid point. There is such a thing called constructive logic that will limit the sets exactly to what you're saying. But we haven't made that assumption, right? So given the two rules,
Right.
right? Even if it breaks, if it's counterintuitive, if we have not been able to refute the infinity as an element, then there's no good reason to reject it, right?
No, but that's what I was saying, right? Because you said that the successor of infinity is infinity.
Yes.
Right, but you haven't shown that infinity is a numeral. Therefore, you cannot say that the successor of infinity is also a numeral.
No. So I'm saying, given that, assuming that infinity is a numeral, then infinity is a numeral, right?
Yeah. Yeah.
Right. Therefore, this set num infinity is closed with respect to the rules.
But that
Right.
involves a tautological definition. If assuming infinity is a numeral, then infinity is.
So, no, I want you to think of it so this is an equation, the rules are equations, and you definitely have systems of equations with multiple solutions, right?
Right.
So this set of equations has at least two solutions, one with infinity inside and one without infinity inside, right? Which one do we take? Obviously, we want to define a unique set. Okay? So now you can make your argument. Since infinity is, right, the argument about infinity is tautological, right? You can say, I want to refute infinity. I want to take the smaller set. Okay? Which is indeed what we are going to do, right? So this is the constructive approach that we want as computer scientists. But be aware that since we might very well define the set as the set of a solution to this set of equations, right? My definition may say, whenever I have a set of rules, any solution to that set of rules, any set that is closed within the rules, is a definition resulting from those rules, right? So definitely in that sense, we're going to have we might have multiple solutions. Okay, so people have been puzzled about this and have wondered about how to restrict the definition so that they would be unique. All right. It turns out that the study of solutions of such sets of rules is a very interesting area. The solutions typically form an algebraic structure named a lattice, right, with a partial order. And it turns out that these solutions will have a least element and a greatest element. Okay, so if you, let me see if I can wipe. Okay, so a lattice is something where you have an element. I'm just going to represent them as points. So this is the bottom, is the least element, and there will be there's a partial ordering. We're saying that this element is smaller than this and it's smaller than this, but it's not necessarily true that this element is smaller than this. There might be elements that are not connected at all. So then we might have some relationships like this, right, where every edge going upwards represents a less than relation. And then there's a top element. So there's one that is greater than everything else, right? So this is now known. Any set of rules will create a set of solutions that are in this lattice. And any of them being a solution might be a correct pick for what is defined by the set of rules, right? So we have to specify one. We cannot add rules. That's the interesting thing. We cannot add other rules to select specifically one of these sets. Very few sets of definitions have unique solutions. So therefore, we go semantically, right? We should now go to take the rules, define the semantics of the rules, and say, oh, this is the lattice defined by the rules, and we are always taking the smallest element. The one that doesn't add any tautological thing, because everything that we would add in there that keeps the set closed would lead to a tautological reasoning. And
so that's
yes?
the representation set of numerals using the infinite. If infinite is not unique, or it's not the smallest way we could represent.
Yes, right? So we're going to pick the smallest, right? So this is the argument I was trying to make, right? So if I put inside infinity plus successor of infinity, which is infinity, then we get, so infinity is not that arbitrary. Actually, we get another fixed point. So we call these fixed points. And yeah, we decide to just pick the smallest. Again, the argument that I was making. And right, so this is where we resolve it. We say it's these rules, it's all the elements added by these rules and nothing else, or the least set that satisfies the rules. Now in passing, typically when you look at the semantics of a programming language, you look at terminating programs. Most algorithms that you study in books are terminating, and actually termination is something we want. But if you think of something like an operating system, that's a program that doesn't terminate, right? Doesn't have bounded execution time. Of course, it terminates because at some point the computer is going to blow, right? The hardware is not going to last forever, right? So in 10 years, 20 years, maybe 100 years, the computer is going to it's not going to last that long. So that program will terminate because of that. But as you look at just the program, the semantics of the program, you cannot say that the program has bounded execution, right? So it's potentially infinite. Therefore, the data structures that you are creating inside are potentially infinite as well, right? Especially if you work with streams of data. And there's plenty of streaming applications nowadays, you must know that. Ticks that are coming from the market into a trader's computer, that's a stream of data that is potentially infinite. It doesn't have a bounded execution, right? So how do we model this? Well, a stream of data is going to be a list, right, that has no end. So it's very much like the successor of the successor of the successor of the successor. How are we going to define an, I'm jumping the gun a bit. How are we going to define a list? We're going to define it as something like cons of the first element and cons of the second element and cons maybe of the third element, and nil. Right? Remember that? Of course, there's more elegant notation for it, but basically this is what it is, right? Cons is a pair, and essentially you have a linked list, first element, and the second element is the tail of that list. So what if instead of nil I just keep going? I put cons and cons and cons and cons and cons. This is very much like the successor of the successor of the successor without really knowing whether there's a zero inside or not. Right? So this is an infinite list. How do I model this? I cannot fit it in my set of rules where everything is finite. So I am forced now to consider the greatest fixed point, the greatest solution to my set of rules. When I do that, and I want the greatest solution to my set of rules, I don't use the principle of induction anymore. I use the principle of, anybody knows? Co-induction. The only difference when we call it co-induction is that the underlying understanding is that from any set of rules we take the greatest solution. Okay, so this is very important in dealing with the semantics of infinite data and of infinite running programs. Just in case you might hear about it, we're not going to look at co-induction at all. But remember that we're putting these rules and we're making the choice of taking the smallest solution. Is just a choice, right? It's our choice. It's not something mandated. We could have very well looked at the greatest solution, and we could have still been able to build a cogent theory, right? As actually some people have done. The semantics of infinite programs is a established field. Okay, but let's keep things simple. So we're taking list solutions, meaning all the elements defined in the rules and nothing else. Any questions? It's like a convention we're making.
Could you
Yes.
explain how the external clauses work?
Well, it doesn't look at the rules. It has nothing to do with the rules, right? The external clause has to do with the semantics, with the interpretation of those rules, right? So if you look at the rules, you would say the interpretation of that rule is any solution, any set that is closed within the rules, right? So the num and the strange num, both of them were solutions, right? And we just make the choice that we pick the smallest one. So that's the extremal. We're taking the minimum, sort of.
There's a qualifier as to like why we're selecting one.
Yes. Yep.
And the extremal clause applies to everything that you put.
Yes. So any set of rules that we put in front of us from now on, the underlying assumption is that what we take the smallest solution to. Okay?
But is that like, so do we need to put an external clause even when there's a unique solution?
Can you bring me an example with a unique solution? I mean, there might be. I might have seen some, but they were contrived enough to not.
Okay.
I would have to look a little bit in my old research papers and to find examples like that.
For the sake of argument, just say that.
No, obviously not, right? But you want uniformity. So things work best when you have a small set of rules that apply consistently, right? You want uniformity. So you want to make this rule across the board. Any set of rules I put on the paper, the underlying semantics of those is a closed set that is the minimum possible. Okay?
But is there no reason we couldn't qualify that rule per set and not universally?
Yes, no, you can, and there are theories that do that, right? Obviously, that will complicate things. No, I mean, so in most infinitely running programs, you would have pieces that you want to. You want to. Yeah, so you have an infinite running program, but you accumulate a certain amount of data, and then you invoke an algorithm on that data, and you want that to be finite because you want to take the results of that and send them over in the output. So that algorithm alone will be finite every time it is invoked, right? So then you would want a finite semantics for the algorithm, but an infinite semantics for the overall program, right? So at that point, you will have to qualify. You'll have to build a theory where you
Right.
qualify every set.
In practice, simpler to have one set of rules for everything.
Well, for us in this course, it's going to be simpler to have one set of rules for everything, right? I mean, we're limiting ourselves because there's finite time. There's only so much you can learn in this time, yeah. But there's no prescribed limit. So if you look at Cox, some of you had some familiarity with Cox, the theorem prover. Actually, you will see inductive and co-inductive in there as keywords side by side, and you will find inductive parts and co-inductive parts in your proofs as you need them, right? So that's one place where actually the theory gets very hairy. Yeah, I mean, let's keep things simple, and if you have the capacity to to complicate them later, feel free to do so. Okay? Cool. So to me, that was the surprise when I saw induction. I was a graduate student when I learned this stuff. It was never explained to me in so few words, so I had to read about half a book to come to this realization and understand that inductive means minimal. When you say inductive means minimal, co-inductive means maximal, and it's only about that, right? Induction is a much more stupid thing than I thought it was before. It's a very mechanical set of rules. And that makes it great for theorem provers, right? The more mechanical it is, the better for a theorem prover. All right, so I'm repeating everything I said. I think this is quite clear. All right, so we've seen inductive definitions, and inductive definitions induce an induction principle. So we're going to uncover an overarching principle called structural induction, but it turns out that you cannot formalize structural induction properly, right? So if you go into a theorem prover, there's no such thing as generic structural induction. So then what do? You define your data structure with induction rules, and then the theorem prover derives automatically your induction principle for the data structure. So you have a specialized induction principle for each data structure, right? But everything comes from this overarching principle, which we can only explain in English. So what we want to introduce here is the fact that with every inductive set of definitions, there will be a resulting or an induced inductive principle, induction principle that we can use to prove properties about that the data structure. All right, so let's look at the structural induction principle for natural numbers, and this we would want it to be the mathematical induction that we used to have. We used to, you know, from your previous course. So let's try to prove the following thing. Any numeral has either parity 0 or parity 1. Okay? So parity is either 0 or 1 for any number. So obviously the numeral 0 has parity 0. And any numeral successor of n has parity 1 minus p, where p is the parity of n, right? Does p satisfy the rules? So the induced induction principle is also an inductive definition, if you want, right? We can write it as an inductive definition. We can say that if p of 0 is always true, right, and if p of n implies p of successor of n, then p of n is true for all n, right? So we can derive this set. We can derive this set of rules, of induction rules. So these would be induction rules, right? but they come from the inductive definitions of numerals, which were 0 and then Pn, not Pn, n successor of n, right? So it turns out that we put a p in front of everything and we just got the induction principle. Okay? And that we can do for any data structure. And then once we have these rules, it's a bit of a stupid proposition, but right? It's very easy to prove now. All right. So this explains the induction principle, which I have just done. So let's see how does it work for trees. So for trees, let's remember the trees. We have empty, and then we have if L and R are trees, then node of L and R, right? So what are we going to do? We're going to put a P in front of empty. We're going to put a P in front of L, a P in front of R, and a P in front of node LR, right? And we're going to say if P of empty is true, and if it is also the case that P of L and P of R imply P of node of LR, then P holds for all trees. Okay? And we derive the induction principle for trees. So let's show that every tree has a height. Again, a bit stupid, but it follows the principle, so it's a good exercise. We're going to define the height first, right? And now, as we define the height, we're going to take advantage of inductive definitions again. So how do we define the height? The height of empty is 0, right? So we can write h empty equals 0, and if h empty, if hl equals let's call it hl, and if h applied to r is h index r, all right, then h of node, and I'm just going to write n of L and R, is going to be 1 plus max of blah blah blah, right? You see it here. So we define the height by means of an inductive definition, right? And we've written it in English. So I've written it down so you can see the correspondence. All right. And how do we prove it? Well, we have to use induction, right? So the property now is that the height of a tree always exists, and we can verify that for empty, because the height of empty is 0, which is a number, and then therefore exists, right? And let's assume that the height exists for left and right, right? So left and right are numbers. The maximum of left and right is a number. 1 plus that maximum is a number. So therefore the height of node of L and R is a number, and therefore it exists. Now you can see a little bit of justification for the rule that we made previously, that we only take the minimal set. The minimal set can always be proven to contain terms or constructions of finite size. So if I have an inductive definition and I look at the solution of those inductive definitions, a set of inductive definitions, and I look at the set of those inductive definitions, the smallest set that satisfies it always has finite constructions. It's an infinite set, but every element inside has finite size. This is an interesting thing, right, to think about. All right, so having made that rule, the inductive principle now looks looks correct, because if I had allowed infinite trees to be inside my solution, then I would have derived a result that is not true. I would have said that the height exists for all trees, but infinite tree was there inside, or a set of infinite trees was there inside, and those do not have a height, right? So that kind of shows that our rule of taking the minimum is a good one. There would be a mathematical proof for why this is a good one, but this is sort of an intuition. We don't want to go up to that level. Is this clear? Okay? Cool. So this is the argument. Sorry, the slides are a bit verbose. I'm reusing slides of the previous teacher of this module. Because, as I explained, I don't want to upset the waters too much. I want to be teaching the same materials. So that's what it is. So this is the proof, right? And it's good that you have it written down, because you might want to go and revise. Let's go and write some code. So we're coming close to the end of class, but we're also coming close to the end of the slides, so maybe we get to write a bit of code. In MES, students are quite familiar with Java, so to keep them in a familiar spot, we present some Java code once in a while. I understand that it's not so relevant to you, so I would rather go directly to the OCaml code. One interesting thing when you make the switch is you kind of start appreciating OCaml a lot more, right? So we're defining a type, right, in OCaml. Yeah, I should at some point explain what a type is, but maybe I'm gonna postpone that explanation for when we introduce types in one of our type programming languages. You can think of a type as a sort of a set, okay? And a language is a language, so you can only create constructions of that language. And think about the fact that OCaml, as complex as it is, actually is defined as a set of inductive definitions. It's a long list of inductive definitions, but it's nevertheless one, right? So inductive definitions allow us to say what the correct syntactic constructs of that language are. And we want to be able to create constructions like this, right? We want to mimic the numerals, right? Even though we're not going to use them in practice, but just as an exercise. And what gives us the ability to do so is the definition of a type, right? This type here will be the set of all such constructions. And if we define it well, it will allow us to write syntactically all the constructions that we need. This very clearly mimics the inductive definition that we had, right? A numeral is either 0 or the successor of a numeral. Notice the recursion. So this very much looks like a recursive definition, as you are already used to have. And then the correct constructions deriving from here are, I'm going to use z and s because it's easier. So we're going to have s of z as a possible construction, right? Z is a possible construction, S of Z is a possible construction. Now this is a numeral, so I can put another S around it. And this is the type that mimics the numerals. And this is the materialization of an inductive definition. There's a little quirk here. The quirk of not having brackets around 0, which might confuse you. So normally you would like it this way, and you wouldn't be wrong in writing that. However, OCaml uses for functions, uses the curry notation, which sounds like the food, but it's the name of a mathematician. So his name was Haskell B. Curry. He's a very famous logician, actually. The first name, Haskell, gave name to a competing programming language. And this led to the definition of the carried. He introduced this definition notation, whereby instead of writing f applied to x with brackets, we write fx without brackets. This has certain advantages, and we're gonna see later what these are. You can think of this expression as an expression where there's an invisible operator here. There's an invisible binary operator here, and we can say f applied to x, and that word applied denotes the invisible operator. This invisible operator associates to the left. That's very important, right? So if I write f, x, y, this looks like a function with two arguments, right? But actually it's a function of one argument that returns another function of one argument, right? So being associative to the left, the natural order of execution is this. F applied to x first, that returns a function which further can be applied to y and return a result, okay? So when we write successor of 0, actually what we would like to apply is, and because, before we go there, because brackets have the meaning of grouping elements together so that it changes the priority of the operators, if I put an x here, if I put brackets around this x, that's not wrong. It's not necessary, but it's not wrong. All right? Nevertheless, normally what we would write in mathematics is successor of 0, right? So notice that the only brackets that we can change, that we can get rid of, are these ones. I cannot get rid of these ones, the ones that I'm underlying with green, because that would change the order of the operations. The associativity of the apply is left to right, whereas what we want for the applied here is to work from right to left. Okay, so we have to write, let me get rid of all the clutter. We want to write it in this way, right? Successor applied to 0 first. This is a numeral, and then successor, the outer successor is applied to this numeral. If we would just write successor 0, OCaml would try to evaluate this first, and this doesn't make any sense. Okay? Okay. So we're going to make take advantage of this feature. We have such a thing called partially applied functions. It's a very interesting feature of all functional languages, and we shall take advantage of that. So get used to the carried notation. All right. This would be a tree in Java, and again, so look at the amount of code that we write, and surprise. Okay. So this is the definition that we need to have. A tree is either empty or is a node of tree and tree. So what happens before we go there? So going back to the carried notation, what happens if I write xy? How many arguments does this function have? 1. Very good, right? Everybody agrees with that? What's the type of that argument? A tuple. Very good, right? So it's a function of a single argument, which argument happens to be a tuple. All right? It's not a function of two arguments. Therefore, right, when we define node here, so node has the semantics of a function. It's just that it's a constructor. It doesn't define any computation. And when I write, going back to the previous slide because that was easier, when I write successor of 0, right, there's no other way to write successor of 0. You might expect, oh, there's a function returns a result. What's the result of successor? No, there's no result. Successor of 0 can only be written as successor of 0. This is what a constructor is. It has the semantics of a function, but it doesn't give you a result, right? So going here, we're going to have to write node of two trees. So we're going to write node, and we're going to have to write, actually you see it here, node empty. So starting at this bracket and ending at this bracket, this is a tuple, right? The comma of that tuple is here. And the second element is another tree, right? Which, so is this constructor applied to a tuple. The tuple starts here and ends here, and this is the comma, right? And the first element of this tuple is another tree. Okay, so we have to, in the type definition, we have to say that the recursive element is actually a pair of trees. And this is how we denote a pair, the type of a pair. So something like 1, 2, which is a tuple, a pair containing 1, 2, will have the type int star int. Okay, that's how the type is denoted. This comes from the Cartesian product notation. In mathematics, you would use the x to denote multiplication. You have set A, Cartesian product set B. In computer science, in programming, multiplication is denoted by the star. So then that's where the notation comes from. Is this clear? Yes?
Quick question. Mathematically, is there any difference in the notation for a constructor and a function, or are they virtually identical?
So you can use a constructor in lieu of a function. The problem is
No, I mean the way they're notated, the way they're written.
Oh, okay. So that's actually a good point. Note that this guy is capitalized. All right. So that's the only difference, really. We denote constants. Constructors are constants. Right. Whereas functions, actually, when you define a function, you take a variable and you assign an anonymous function to it, right? So functions will be, in fact, variables holding anonymous function values. But this is a symbolic constant, and all symbolic constants in OCaml start with a capital letter. But semantically, they're not, right? Because it's a function that I can apply to an argument. There's no result other than the expression resulting from that application, however, right? So that's the important thing to take home. So now we're going to use a lot of trees. Generally, languages are processed in a way in which the program file, the text file, gets converted into an abstract syntax tree. And that abstract syntax tree is a data structure. And inside the memory, it will look something like this. But we never have to see that in front of us unless we do some debugging. But even then, we can restrict what we see of a data structure quite a lot. So typically what we do is we take the file, we get this object which sits in a variable. It is very complex if we were to look at it, but we don't quite look at it. We decompose it and process it, right? And to that end, we are not so affected by the fact that we deal with very complicated notations in order to define data structures, right? Because this is quite cumbersome. For the data structures that are very common, namely lists, there is more elegant notation defined there. Okay, so this is pretty much what I have already explained again. Note that there's a very clear mapping from the inductive rules to the type definition. Okay, and that's going to be one of the advantages of OCaml. So where is the extremal clause? If we're taking the rules and defining them in the types, where is the extremal clause? It's in the implicit semantics of OCaml, right? As well as Java, because it's still a Turing complete machine. Can we deal with infinite data structures in OCaml? What do you think? Sure, we should be, right? Because it's a full-fledged programming language, and if we should be able to write operating systems in a full-fledged programming language, right? So non-terminating programs. The way it deals with that, I don't think we're going to cover that, is by using lazy explicit lazy evaluation. There are two functions called delay and force. Have you ever had a chance to look at those? Seems that some did, some didn't. No. Well, there's plenty of material on YouTube if you just go and say lazy evaluation. If you're interested, I can have a small detour, but it wouldn't be part of this course. So let's look at the definition of height. All right, and here we introduce pattern matching. All right, so this is a construct for Camel. It is specific to functional languages. Languages like Java don't have anything like that. It makes for very convenient deconstruction of data structures. All right, so we're going to say I want to compute the height of a tree, and I'm going to say if T is the tree, well, match T with. What are the possible formats of T? Well, it can be either the empty tree, right, in which case the height is 0, or it's of the form node LR. So notice that whenever I match with something like this, I'm going to go to the previous slide now, or a few slides behind. Whenever I say match with node of LR, right, so we have a rule, node LR, and go execute some code, right? So this guy is going to become L, and this guy is going to become R. So L and R become variables that automatically bound to the segment or the piece of the data structure that would fit in that placeholder. Okay, so we're matching. We're seeing, let me change color. We're seeing node matches with node, and bracket matches with bracket. And now I have a variable, and here I have a constant empty, right? So automatically I'm going to create a binding L to empty. And then comma matches with comma, right? And then I see something else, and that has to be matched with R, some other term, and I'm going to say R matches node of whatever is there, right? And then bracket matches with bracket, and the matching is done, right? So by using this pattern matching, which is a structural tree matching, we can extract components of a data structure and process them. This is generally very convenient, makes programs a lot more concise, right? So look again at the definition. The height of empty is 0. The height of a tree of the form node LR is 1 plus the maximum of the height of L and height of R. Notice the recursion. You probably don't have a problem with that. You must be experts at that. And notice that there's no other rule. We only have these two rules. This also follows from the fact that the set of these constructions has nothing else, right? It's the minimal one. There's no other rule to add here. There's no other matching to do because there's nothing else in the set. Is this clear? Now, there's a bit more to add here. So if you input this from in the interactive environment, you will have to add this double semicolon at the end of each line. Everybody's familiar with that? Cool. And then, on the other hand, if you have this entire piece of text inside a file and you want to compile it, simply writing print end line will not work. You have to assign it to an anonymous variable. So if you're typing it from the interactive environment, you can leave this one out. All right, but if you're inside a file that you want to compile, you actually can't do that. You have to use the anonymous variable. By the way, anonymous variable, and everybody knows what that is? It's a variable that is only used once, and therefore I don't have to give it a name. I can use it anywhere I want, whenever I define something. So for instance, if I weren't interested in the value of L, here I could have used the underscore as the anonymous variable, right? Obviously, then I wouldn't. My definition would not be in terms of L. L would be completely ignored. Is that clear? Cool. So, in summary, we covered inductive definitions and we looked at induction principles and we saw how that translates into a camel. The time is pretty much gone, so I'll probably stop here. I will every once in a while do a little video recordings and add to the explanations, especially if you have doubts, and if you express those in the forum and I know what they are, then at the end of a week I can look through all of them and make little tutorials with the very specific things, because we don't get to see face to face that often. I'm going to try to have some office hours if they give me a room and a place to be, and we can meet a couple of hours a week. But since I'm not here whenever you need me, then we should try to make the most of whatever communication means we have. So if you tell me what your doubts are, I'm going to try to provide little lessons with how to do everything as a video. Okay, is this clear? Any questions? Yes?
I'll show you interesting. I saw the email that dropped the prop.
Yes, call me Razvan.
Okay, right.
Yeah. Yeah, so since we have the forum now and IVLE, probably it's best that we keep to those. So, I mean, feel free to chat me up on Hangouts if you need something very quick and you need me urgently. But other than that, it's probably best that we stick to IVLE, because that's archived. Next year, students might want to go in and learn something from the experiences of this year. I'm going to stop the recording now, because since I'm putting this on YouTube, perhaps not